All right. Well, hello, good evening, or I suppose good afternoon or morning, or whenever you're watching this. Hope you guys are doing well. Don't forget there is a Schoology assignment today as well. So you can watch these videos and then do that Schoology assignment. It is over just some practice with sequences and arithmetic series. So just a few questions there, I think. If you give those a go and work on them today and over the weekend. And then this stuff here, you'll have some worksheets over this on Monday. So whenever you get a chance to watch this video. So we've talked about arithmetic series, and so now we wanted to talk about geometric series. And so this is a famous little story here of a, whether it's true or not, I don't know, right? A famous story involves a soldier who rescues his king in battle. The king grants him any prize, within reason, from the riches of the kingdom. The soldier asks for a chessboard with a single kernel of wheat on the first square, 2 kernels on the second, 4, then 8, and so on, for all 64 squares of the chessboard. And so the king decides that the request is reasonable, because the king obviously does not understand exponential growth. And so if we look at this sequence, right, it's doubling each time. So our sequence is 1, 2, 4, 8, 16, 32, etc. So the common ratio is 2. And so the question then is, how many kernels of wheat will the soldier receive? So notice that that is the sum of all those values, right? That is not just how many kernels will he receive on square 64, right? That would be the sequence, and you'd just be finding the 64th. But we want to know the total of all the wheat, right? That's obviously not going to fit on this chessboard because we want the sum of all of that, right? And so again, that's called a series, okay? So we want to do this, and so this is a geometric series because this time you have a common ratio. So instead of a common difference, we have a common ratio, right? And so if I look here at my pattern, right, what I'm saying is I'm adding up this geometric sequence, so therefore it becomes a series, and so right, we're adding up 1 plus 2 plus 4 plus 8 plus 16 plus 32 all the way out until we get to the 64th term. So notice that the 64th term, right, is actually then 2 to the 63, right, because recall that you would have only applied the ratio 63 times since you're to get to the 64th term. And so that is going to be a very, very, very large number. Okay. Now, one way to calculate it is on your calculator. Your calculator actually has the ability to do sigma. And so you could pull up the sigma notation, the sigma key on your calculator. Or the other option is it's in the menu. So you can pull that up and actually just fill in all these key pieces and you will get it. Okay, but we want to actually learn a formula as well. And so I'll allow you to do that because I honestly don't have my calculator here right now. And I can tell you that it is a really big hashtag, aka number. Okay. I'm a little out of it. I was the bear tonight at the senior. As the seniors came to pick up all of their stuff, I was in the bear costume, which was really fun, but I'm really tired right now from wearing the bear costume for 3 hours tonight. Although it wasn't too hot, but my neck hurts from wearing the head. Anywho, so that was fun. But it made me tired. And then I realized I still have to record this video. So, so let's take a look real quick at where we get the formula for a geometric series. Okay, so this is just another formula. And so the way it works is, if we think about, right, if the sum of a finite geometric sequence, aka a geometric series, we could write that as G1 plus G2 plus G3 all the way till we get to the G sub n term, right? We're adding up the first n terms, okay? And so since we know that the explicit formula for the nth term of a geometric sequence, so this is what we learned a couple days ago, right? That to get the nth term, we take the first term, G1, and multiply it by r to the n minus 1. So right here for that G sub n term, we're just replacing it with the formula. So the sum of the first n terms is G1 right, plus, so now rather than writing G2, notice that what I did was I wrote it as G1 multiplied by R, right? Because that's what it would be, okay? And then G sub 3 would be G1 times R squared. So I'm just replacing, so instead of writing it as G2, G3, I'm just replacing it with what term it is in the sequence based on our formula, okay? So now here's the sneaky part. So what we do is we then decide to multiply that equation by R. So when we multiply that equation by R, then down here, right, the left-hand side would just get multiplied by R, so it would be R times S sub n. And on the right-hand side, when we multiply by R, then G1 now has a R, right? And then this one, since it was G1 times R, when we multiply by R, now it's G1 R squared. And then when I multiply this one, it would be G1 R cubed right here. Right? And if I go all the way out, then this term here, the very last term, when it gets multiplied by R, right? If we think about when that one gets multiplied by R, that's R to the first. And so you would add the powers, right? N minus 1 plus 1. And so it becomes G1 times R to the n, right? So what we end up doing then, so this is the clever little thing, after we multiply that, is we actually then just subtract this equation from the one above it. Right? So if we do that, then we get S sub n minus R S sub n, right? That's what the left-hand side would be, equals, and you may say, well, Mr. Chandler, how in the world am I going to subtract this if I don't know how many terms there are? But look at the pattern, right? So if I go to subtract this, then G1R1 would subtract G1R1, and G1R squared subtracts G1R squared. They all end up canceling out except the G1 minus that last term, G1R to the n. So all the other terms drop out. So then all we do is we say, oh, well, on this side, let's factor out the S sub n. Right, so we suck that out. And then over here, a lot of times we'll also suck out the G1. And so then to solve for S sub n, we just divide by 1 minus R. So our formula for the sum of a geometric is G1 times 1 minus R to the n all over 1 minus R. And that's our formula, okay? So that's the sum of a finite geometric series. So there's the formula again. For whatever reason, when I typed this up a year or two ago, I accidentally used A1 instead of G1, but it doesn't really matter. But if you want to keep it straight, you can use a G1. Notice what's interesting about this formula is that it only requires the first term and the number of terms. It does, and the ratio. You don't actually need to figure out the last term of the series, which you normally would do with arithmetic, right? So going back to the last question up here, a really big number, right? Well, the first term was 1, right? 1 minus 2 raised to the 64th. There's 64 terms all over 1 minus 2 equals that really big number. Okay, so there you go. All right, so let's just try a few of these. So number 1. So what's the sum of the geometric series 4 plus 12 plus 36, yada, 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 until I get to 2,916. All right, well, how many terms is that? So it's 1, 2, 3, 4, 5, 6, 7 terms, right? So S sub 7, so we know we're adding up 7 terms, is going to equal, so it's the first term, so 4, 1 minus R raised to the n. So what is R in this case? So I'm multiplying every time by 3. Right? So R is 3. So 1 minus 3 to the 7th all over 1 minus 3. I would say that the number one mistake that people make, though, with the geometric series formula is messing up just when they're typing it into their calculator, right? So this is 4 times 1 minus 3 to the 7th all over, whoops, negative 2. Right? And so then we can type that into our calculator and see what we get. So let's see, 4 times, oh, I don't know if I have my calculator up. There it is. Oh. Sorry. Okay, we'll go back to Notability, and then we'll hopefully get this thing to pull up. And it's not liking that. Okay, well, I don't know why it's not working. Okay, so 4 times, I wanted to do a split screen, but it wasn't working. 1 minus 3 to the 7th. Right. So that is that big number. And then divided by, so negative 744 divided by negative 2, right? So negative 2. So 4,372. 4,372. There we go. 4,372 is the sum of that series. Now, you might say, well, Mr. Chandler, those were only 7 numbers. I probably could have just typed that into my calculator. Yeah, you're right. You probably could have. So that's the thing about the geometric ones. If you get much bigger than, a few terms, it starts getting so large so fast because it's exponential. And a lot of times, you're not going to have to add up that many terms, and you're probably right. You could just add them up on your calculator. But there is a formula. There's a formula for that. Oh, boy. Oh, swell. Oh, golly. All right, so I miss you guys. So let's sum this up here. So we're summing up from 0 to 11. Now be careful, because notice that this time on this problem, it's starting at 0, which means how many terms are there? Ooh, there's actually 12 terms, right? Okay, so if I'm going from 0 to 11, so I got to be careful there. So that doesn't happen too often, but you got to watch that. So if I plug 0 in, right? So if I'm summing this up from 0 to 11, and it's 3 times negative 1.5 to the end, then when I plug 0 in, right, then this would be negative 1.5 to the 0 is 1, times 3 is 3. So the first term is 3. Right? And then when I plug 1 in, right, then I am multiplying 3 times negative 1.5, which would be negative 4.5. Right? So, and then when I square it, right, so then I plug 2 in, so I'd be squaring negative 1.5, so now it's going to become positive, right? So this time my common ratio is a negative number, negative 1.5. So what that means is that as I do this, it's going to alternate between positive and negative. But that is totally fine. There's nothing wrong with it alternating between positive and negative, right? So 1.5 squared is 2.25, right? And then times 3 would be 6.75. Whoops. And so my next term will be negative, etc. Right? So let's use our formula though. We want to add up 12 terms. The first term is 3. So now be careful, because a lot of times people get confused here because they'll say, well, wait, I thought that this was when n was 0, not 1. That's true, but this is still the first term, right? 3 is still the first term. It's just the term we got when we plugged in 0. But because it's the first term we get, we still call it the first term, even though we got it by plugging in 0. A lot of times that can be confusing. All right, so we've got first term is 3. 1 minus the ratio, which is negative 1.5, raised to the 12th, because there's 12 terms, all over 1 minus the ratio of negative 1.5. Now, this is where we get some mistakes. You've got to be very, very careful here, because on the bottom, 1 minus a negative would make it a plus. So this would be 2.5 on the bottom. But up top, order of operations, right? Be careful. This is not going to become 1 plus. It's going to be 1 minus still, right? Because when I raise negative 1.5 to the 12th, it's going to be a positive number, right? So then this is actually then just 1.5 to the 12th. So it is not going to be negative negative as a positive on the top because the order of operations there, okay? So let's punch that in. Okay, so my first term was 3 multiplied by 1 minus 1.5 to the 12th. Right? There we go. Let's see, and then on the bottom it was 2.5, right? So the sum of this is negative 154.5-ish, right? So this one, round it. So negative 154.5, okay? So notice then that, when you only go out to 12 terms, it came out negative. What's interesting is, right, watch what happens if I change it to 13 terms, right? Okay, so it's still going to be negative. What's going to happen when I go to 14 terms? Oh, still negative, okay. But let's say, what was it after 10 terms? Negative. What was it after 9 terms? Negative, okay. All right, let's see. What was it after 7 terms? Negative. Okay, maybe I'm proving myself wrong here. 6, negative. Usually, when they alternate like that, I'm just going, yep, still negative. The negative numbers got so big so fast that they canceled out the positive. So I guess what I was going to show you is worthless here. So never mind. All right, so I've just gone off on a horrible tangent for no reason. All right, so our original answer was negative 154.5. Negative 154.5. What I was going to say, negative 154.5, is, right, that because you're doing positive, negative, positive, negative, positive, negative, that, after sometimes when that happens, for the first few terms, it'll add up to a positive number, then it'll add up to a negative number, positive number, negative number. But in this case, the negatives got bigger than the positive numbers faster. And so essentially they just added up and became negative pretty quick. So, all right, so number 3, last one. A game show is offering a prize of 1 cent on the first day, 3 cents on the second day, 9 cents on the third day. What's the total amount of money that you earn from this prize in 2 weeks? All right, so our first day then, right, is 1 cent. Well, that's great, okay. But then we earn 3 cents, and then we earn 9 cents, right? And that continues. And so we have right, what are we multiplying by each time? We are multiplying by 3, right? So our ratio is 3. So we want to do it for 2 weeks. And we will assume that this game show happens even on the weekends. So let's do the first 14 then. So for 2 weeks, we'll do 14 days. So on that first day, you only got a penny, 1 minus, but your ratio is 3, right? And then 3 gets raised to the 14. And then on the bottom, we'd have 1 minus the ratio, which is 3. So let's see how much money you would have. All right, so we'll go back to good old calculator here. So 0.01 cents, right? times 1 minus 3 to the 14th. And that's going to be divided by 1 minus 3. So, check it out. It seemed like you weren't going to have much money, right? But as long as you stuck around at the game show long enough, you actually end up with $23,914.84. $23,914.84. Not bad for 2 weeks' earnings, right? So this is exponential growth, right? It grows fast. This is why, if you remember that Planters peanut guy coming in, or Monopoly man, not the peanut guy, the Monopoly man coming in and offering you a salary, right? When we first started exponential growth, right? And so it grows really, really fast, right? So I hope that makes some sense, even though I was a bit tired and out of it tonight. And I will talk to you guys soon, and enjoy your weekend.